throttling process. So this involves an expansion. So I have a fluid coming pressure Pi initial or the inlet pressure, and P naught is the outlet pressure. So since it's an expansion process, where P naught is less than Pi. So the question is, what about P naught? Less than Pi or greater than Pi? So clearly the purpose of the throttling process is to cool the fluid typically. So we would like T naught to be less than T. So that would roughly mean that dT by dP must be greater than 0 for cooling to take place. Both the temperature and the pressure will decrease across the tube. Right? So we have to calculate it. The whole activity is expressed in terms of the equation of state and the specific fields. Right? So here we take into account the T and H, and we already have expressions for the derivatives of H with respect to T and E. So we can regard T as a function of T and H as arising from this, assuming suitable invertibility conditions are satisfied, and clearly the derivative dT by dT at H is minus dH by dT at T. Right? So where we this is minus 1 over Cp, and just by looking at this you can see this is actually 0 for an ideal gas. Because we know that for an ideal gas, dH by dP is 0. The enthalpy doesn't depend on the pressure. In the ideal gas, what it means is that whatever may be the expansion, degree of expansion, temperature will not change. Gas behaves like an ideal gas, simply cannot be cooled by the Joule-Thomson process, nor can it be heated because its temperature will remain is insensitive to pressure variations. That's what it means. So then dH by dP, we already have a formula. So this is dP by dP. Also be written as minus 1 over Cp. If you look at the other set of formula that are given in terms of the beta and the kappa, you can write this as B times 1 minus P beta. And we know that the beta is actually equal to 1 over T for the ideal gas. So even if you haven't recognized it here, or you can calculate this and easily verify that Joule-Thomson coefficient will vanish for the ideal gas. What makes the whole effect interesting is the fact that this can actually vanish at isolated points. For ideal gas, the dH by dP is identically 0. But for other fluids, it so happens that that point can vanish at certain points, right? And those will turn out to be regarded as the, in fact, the condition for that is either beta is equal to 1 over T, right? Or we can say T dT by dT. It typically happens that there is a maximum in the temperature versus pressure diagram. So what does mean? This is all it's constant enthalpy. So once I fix the inlet conditions, the enthalpy of the fluid is fixed at all points, right? So if I plot T by enthalpy. And so the enthalpy is fixed. That means it is equal to some h on to a star, let's say. You get a curve on the temperature pressure wave, and then typically to show a maximum, it can be shown that this will have a maximum. Now the important thing is that if you see with regards to an objective of cooling, right? So now the pressure is going to decrease, right? So if the, let's say the pressure is here is Pi, where is P naught going to be? To the right or the left of I?
After the maximum.
To the left, right? So P naught will be somewhere here, and clearly this would correspond to a decrease in temperature. We have accomplished our objective. However, if suppose I choose the condition so that, let's say, Pi is here, right? Now you can see, let me mark this point where it is. So this is going to be the inlet temperature. So this is going to be Pi. And I fix Pi and I say that this enthalpy of the entering fluid corresponds to this enthalpy. So this is some H equal to some H star, let's say. Now, depending on the degree of expansion, for instance, the degree of expansion is such that P naught is only here. You can even have a heating of the fluid. So we have to make sure that the degree of expansion is such that if you want to cool, right, you have to make, you cannot just blindly feed the fluid in without paying any attention to the degree of expansion. So it is important that if your inlet temperature is to the right of the inversion temperature, then we have to be careful in making sure that the sufficient expansion is provided so that there is a cooling effect. Otherwise, the fluid might even get heated. So we need at least an expansion further from this, right? So that the fluid is cool. Otherwise, we will have the opposite effect, right? So that is why finding the inversion temperature is very important. Right? And the inversion temperature there is a profile of the inversion temperature at various values of the enthalpy, which we will see later on, because we need to really to make sense of this, we need to be given an equation of state. So later on, when we look at particular equation of state, we actually construct we show how to construct the inversion temperature profile. Because what will happen is typically what we have is that at a lower temperatures and pressure, the inversion temperature will typically move like this. So the inversion temperature profile will look like this, and then it will turn back again. Right? So we will see this profile later. So what is important is to understand the role of the inversion temperature and what its relation to the Joule-Thomson coefficient and its relation to the whole purpose of cooling the fluid. Right? So if you look at further, Calvin has an extensive discussion of that. You can go on. We revisit this when we get to familiar with specific equation state, where we show how we can actually construct the inversion temperature. So this is just a preliminary discussion. Are there any questions? Yes.
V0 should be less than Pi.
V0 should be less than Pi. Huh? Yeah, V0 should be less than Pi.
So the curve is decreasing.
Huh?
The curve is decreasing.
Forget about the curve. We are talking about the pressure at the inlet and the exit. Right? So, V0 is always to the left of Pi. That's correct. I don't see any contradiction with the curve having a maximum. Right? constant enthalpy contour. It's like a contour plot. So that is what it is. So depending on what Pi and P naught are, so you will get different temperatures at the exit. That's what it means. So once I have fixed Pi and Di, and then I also fix the enthalpy. So I choose, now the enthalpy is going to be fixed for the entire process. So I focus on that curve. Let us say this, that value of the enthalpy that I have plotted, right? So now I have to place the Pi, P naught. So once I place Pi, automatically Pi is determined by this curve, on this curve. That corresponds to the actual enthalpy of the fluid. Then P naught, as you are saying, must be to the left of Pi. P naught is always less than Pi, right? But the question is, what happens to T naught? That is what we are saying. T naught need not necessarily be less than T, because typically the fluid show the inversion effect. Other than the ideal gas for which everything, nothing changes, the temperature will just remain the same. Right? So that's what you have to keep in mind. So we come back to it later, and now we start with the assignment problem. So what I'll do is take one of the problems that's given. This is given a fundamental equation, how to get various other quantities, like the temperature, pressure, and specific heats, various other fundamental equations, and so on. So I'll just take one example. The first problem. So what you are asked are first P of dE. So that's a very useful quantity. Normally, we are not given. We also look at the reverse problem. Given P as a function of B and T and some other information, how to construct fundamental equation. But these are more like textbook academic exercise. In that, given an equation of state, or rather a fundamental equation, which is supposed to have all the information, our idea is to get various other useful quantities. One of the useful quantities is clearly P as a function of B and T. We are also asked to get P as a function of B and T. So how would you go about doing this, right? So can you come to the board? How would it proceed? First, we need to know how temperature and pressure can be obtained from the fundamental equation. Yes. No, wrong. TVS minus PDV. The others can do it on the notebook. Very straightforward problem. How do we proceed from now? What do we have to do to get P as a function of B and T? P is here a function of S and B. We have to get it as a function of E and T. So how would you do it? obtained as a function of b and t from the second equation. Yes? Yeah, this one, that one. Yeah, write s as a function of b and t. So clearly, B naught, you are not given B naught is some characteristic volume, B dash probably some characteristic temperature. From there, I probably got it from Calvin. It didn't give me what these mean, right? But clearly, those are all constants. It's not given clearly in the assignment sheet. You have to assume. Yes. So get S as a function of B and P from that. Very simple. So what you have to know is that we might not always be able to invert like this explicitly and get it, right? But these are some simple examples which will help you go through the process and achieve this. Yes, how do you get S as a function of B and P? Very straightforward. P is given as a function of S and P. So how do you get S as a function of B and P? S as a function of B and P from that. R is clearly the universal gather must be. Okay, so yes. Why is it so difficult? S is a function. From this, I want you to write S as a function of B and T. Yes, can you come to the book? Use. S as a function of B and T. Yeah. So now substitute and get the answer. Yes. You got it. Yeah. What is this? 5. Yes. Yeah. So now substitute it into this P. Yeah. Substitute P. What P as a function of B and T. Right. So it's very clear. The idea is to get P as a function of B and T. Right. So what we have is P as a function of S and P, right? So to get P as a function of B and P, I need to express S as a function of B and P, and here P is given as a function of S and B, right? And so I have to try. It might not always work out, but here it's very easily invertible. We take the positive root of that. Yeah. So we've got somewhere. Yeah. Yeah, that's fine. So clearly, what I want is, rather than, for instance, in a quiz, if I ask this question, if you leave it like this, I may not give you the full marks. You need to group together. Clearly, I can see that there are so many translation possible. You have to simplify to the extent possible. Not just leave it as a mass of quantities and expect me to figure out how to get to the final expression, right? So first thing I would want to do is identify the functional dependence of P on B and T, right? So clearly what we have here is I have P power 3 by 2 times divided by P power half. So clearly dP by dt is greater than 0, dP by dV is going to be less than 0. That much it is satisfying, right? And then I have a whole bunch of coefficients. I don't know how to do it here, but I have the expression, and it turns out to be so what if we put everything together, making something like this? That's all the constants are. I would like to bunch them together and put it in a decent form, because we want to further use this expression. Then we need to be, otherwise you're just getting bogged down in a whole bunch of factors, right? It's important to simplify. Now, how would you get E as a function of E and D? same procedure, right? E as a function of B and T, you can get by, I have E as a function of, I have E as a function of S and B. We have seen it's expressed as a function of B and T. So substitute that, I get E as a function of B and T, and that turns out to be not quite simplified, but yeah. So that's what we have, right? So you can clearly see how it depends, and we can also get CV, for instance, from this. It's fairly straightforward. You can see how CV depends. It might not be very typical, as I'm not sure if these really correspond to any real fluid, but it should typically, the authors of these books would take expression at least satisfy certain important properties. For example, you don't want to have fundamental equation which for the dp by dt is actually greater than 0. That means there's something fundamentally wrong in that equation. So some of those inequalities which we later on derive as a consequence of stability criteria, they are important to assess whether a given fundamental equation is actually satisfying the minimum properties required of any substance. So this is what it is. Now I can ask other questions. For instance, how we can get A. That's very easy because we have already got E as a function of V and T minus P. And I have also got S as a function of B and T here. Very straightforward. So when I say, for instance, fundamental equation for A, you have to know that you have to express it in terms of T and B. Because you cannot E is alpha given. If you just put A equal to if you leave it like this, you get 0 in a quiz. Because when I'm asking for a fundamental equation for A, it automatically means you should know that it has to be expressed in terms of T and B. Right? That is correct. You give the correct value of A, but it's not a fundamental equation because it has so many variables. S, T as well as T. You should have only B and T. Right? So you have to understand. Yes?
Some question on can we do it like using Maxwell equations? Like the integration of like A is equal to integration of minus S dt minus integration of dt.
Yeah, you can do it, but the point is that that integration, right, is a very complicated way of doing it, and it might not always work out. Because for that to work, since you're saying you're going to do it like this, then if you have to carry out this, this is very complicated. You have to choose a proper path, right, between 2 points, and then unless S is a function of T alone, you cannot integrate that easily. You cannot separate the integration. How are you going to do the integration? So that's a very roundabout way. It's not required here. That is typically useful when you want to calculate a change in A between 2 states. Then we have to do that integration, whether we like it or not. Here it's not needed because you're given E, you're given S, but you just calculate A. Very simple from the definition. Right? So let's look at other H. Again, its definition is P plus PE, the expression. But H you should know is a function of S and P. So I have to get this as a function of S and P. P is as it is, and P also I have to get as a function of S and P. So So how do you get E as a function of S and P? How?
TDS minus PD.
Huh? Yeah, come and do it. Not TDS minus PDB, but I wanted to express E as a function of S and P. First objective you should know what you have to do. Yes. No integration required anymore. No, you do it on the board. You can do it there, but I want now to do it on the board. So I have clearly, objective is clear. E as a function of S and P. Obviously I look at this expression. Might be updated several methods, right? But I have already E as S is given as a function of S and B. All I want is B as a function of P and S, right? P as a function of P and S is obtained from here, very easily. So how do you get that?
So we know it TDS minus PD.
That is what you writing is totally meaningless. That is the differential. What I'm talking about here is the actual internal energy. I don't think I have any clue what is going on. It's been found, that's true. It's already given to you in terms of S and B. Now I want you to write in terms of S and P. How would you do it? Right? You have to think a little bit, that's all. Can you come and yeah. Purpose is clear, right? Purpose should be clear. I want E as a function of S and P. I already have E as a function of S and B. So all I have to do is express B as a function of S and B. Right? We're doing it purely algebraically here. We're looking too much at the significance. Because this might not really correspond to any realistic substance. But just going through the mechanics of this so that you know roughly what is involved. Right? So P as a function of S and B is given. Yeah. So that yeah. So that is clear, right? And fine, that's all. Right? All you have to do is express B as a function of S and B. I have E already as a function of S and B, and this will again apply the same. All I have to do is to get this one equation that's already there available, right, from the second of those equations. And so the answer I have, but I would like you to check because sort of scribble down the answers here. But and what I'm getting is a very compact expression for H. Theta by R squared S cube P sort of seems to simplify quite well the two terms, and you get this one expression which is all of them I put under the I separate the constants from the variables. So what I have is here this. You can check this. I don't want you to, I don't want to waste time now just going through the motions, but I'm giving you the answer. Later on, I'll give all the other answers also in a separate answer sheet. But you can easily work this out. Now the other one, G, it has been defined as in several ways, right? But one easy way would be to note that G is A plus PB. Now G I want as a function of P and P. So A already is a function of P and B that we have. Right? I might not have written it clearly, but we have that. And so what I want is B as a function of P and B. That is already there. Right? I have P as a function of B and D somewhere here. Very easy to get B as a function of P and B. Plus B. And again, you seem to get, you have to check on the coefficients and all, but I'm getting G to be minus this, but I check all these answers and give it separately. But you can just verify whether these are correct or not, right? So this is what, for instance, I can ask out of CP already we have seen. CP, I can ask how to get CP. So for that, obviously one way to get CP, well, I have either you get it from, or I leave it as an exercise for you to do. Right? Either you express H in terms of T and P or S in terms of T and P. You can do both and verify whether your answer is correct. So you can get all properties, and the whole idea of this exercise is to show that from the fundamental equation you can get all possible properties. The equation of state, E expresses a function of V, is very typically what is required, and also the specificities and various other fundamental equations. Now what I would like you to do is to try the same procedure for the other two equations given and see if you can in fact invert so easily and get the explicit expressions for all of these quantities. It's just a simple exercise. You just, objective is clear. What you will get are T and P as functions of S and B. Given T as a function of S and B in all the cases. You get T as a function of S and B, P as a function of S and B. So from that, you have to get all other possible functional representations, right? So that's what is the objective. Any questions? So I think if you do even one of the other two examples, you should be able to do pretty much any other problem in this set. Next question is all possible various derivatives of A. You're given, for instance, you're given typical processes that you consider: isentropic, which corresponds to a reversible adiabatic, and then you have isenthalpic, which we've already seen, a throttling process. It's a constant enthalpy, and then there's another constant isentropic. Constant S. You should know what isentropic means, first of all. It's a constant entropy process. Isentropic process. That means throughout the process, the entropy of the fluid remains the same. If you have a fixed mass of fluid, that means the specific entropy remains the same. This is take one example where this occurs in the process. Adiabatic plus reversible. We all know that because from the only expression dS by dt is QR by T, that's valid only for reversible processes. Right? We have seen, otherwise you have the inequality. So we cannot conclude whether it will be isentropic. So if the process is adiabatic and reversible, then this expression holds, right? So where if you are 0, ds by dt is 0, so the process is isentropic, very easy to prove. However, if it's not a reversible process, then you have this, provided again the definition of the fluid is the same throughout, so Clausius is inequality. And so if the process is adiabatic, we can only say that the entropy will increase in the process. It will necessarily remain the same. So you have to be very careful. Not for all adiabatic processes, the entropy will remain the same. Right? So then what we have is an isenthalpic, which is often referred to as a sudden expansion in the flow process. Sudden expansion is called as a throttling process. Constant H, we have already seen one example through the Joule-Thomson coefficient. The other one that is given is what is called as a free expansion. That is generally taken to be a constant E process. So free expansion, and that this will take some time to, we have to look at the first law for the flow process to show that This is isenthalpic, but this free expansion is again a fixed mass of fluid, a closed system. That can be easily proved by I'm not sure if some other qualifications are there, but free expansion typically is a constant E process. It can be constant internal energy. So what you are asked to find are these coefficients, dt by dt. Expressions for these derivatives. You are not given anything, which is kept fixed. So obviously, you know, if I first case isentropic, I would correspond to entropy being fixed, right? Or if I want to look at the isenthalpic, it would be H being fixed. Or if I want to look at free expansion, E would be fixed, right? So you have to get these derivatives for these processes, right? So that is the objective. So you've got some 9. Here's how the temperature changes with volume or with pressure and so on. Right? How the pressure changes with volume. Then we have already considered, for example, dt by dt at S. If I take that, we've already seen, you know, we worked a lot with S as a function of B and D, so clearly we can get what that is. Right? Very easy. Same thing with dt by dt at S. That would involve the specific heat and constant pressure. dP by dt at S, we saw this in the propagation speed. This is to lead to what is called the isentropic compressibility. Right? The isothermal compressibility is -1 over V. Isentropic compressibility is, but this is simply the inverse of dP by dV at constant S, and we've got expressions already in terms of the equation of speed and gamma and so on. So we won't worry about that. I've also looked at the enthalpy. We've taken at least one example, so I'll let you do the other ones. So let's look at that, right? So if I want to do this, this is very easy. E of dt I look at, right? And dt by dv will simply be minus E by dv. I can sort of write this from memory, but this formula you should remember or get it quite quickly. So this would be very straightforward expression. Now for dt by dp, and E I have considered E as a function of P and D, right? So this will work, and it won't be obviously equal to this. We've already got these derivatives. If we look at the expression that we have derived, we have shown what this is and what this is. Right? So we can easily get the final answer. So I'll again give you the table of these coefficients. The last one, dP by dt. My data, because you know, point that I would want you to remember is this will be important in specification of variable. Why we didn't quite consider something as a function of B and D or something as a function of P and D, but didn't consider anything as a function of P and D. We can always consider, right? The point to know is that if you look at the fundamental equation and what it means, fundamental equation, there is a set of independent variables. What this means is that, because we said that from the fundamental equation I get all properties of the system in equilibrium, right? However, to do that, I need to specify a particular state. I have to give you what the state is. So if you are considering the fundamental equation for internal energy, then I have to specify what the entropy and volume of that state are. If I am considering the Helmholtz free energy representation, then I have to specify what the temperature and volumes are. Right? By considering the enthalpy fundamental equation, then I have to specify what the entropy and pressure are of a particular state. So I have to give that. So if I want to calculate the temperature of that fluid, I calculate dE by dx, but I have to substitute something to get a proper numerical answer. I have to tell what the state is. And similarly, so from this stems the common statement that two variables are sufficient to completely pure substance, two properties is sufficient. But these developments also show that there cannot be any two properties, right? It has to be, you have safe if you specify only, if you restrict your specification to these four sets. And that is why this and this are preferred usually, because it's easy to specify the temperature and pressure or the temperature and density of the system rather than the temperature and the entropy and pressure of a particular fluid, right? So, because these are easily measurable, easy to measure, right? So you can ask, well, what about PV? Or for that matter, PS? Because some books it will say two variables is sufficient. Now you will find that normally you can, this is again has to do with invertibility. Normally they might be okay, but you have to be careful. Clearly to water around 4 degrees, P and B are not sufficient to specify that you can easily verify that. We saw that, for instance, we saw that at 4 degrees centigrade, P to 1 atmosphere. So I am specifying P, right? The volume undergoes a minimum, right? P, and suppose let's say I specify the volume or the density. Maybe there are two states that correspond to the particular P and B. So I can take this to be the P naught, and I can take this to be the B naught. This doesn't usually happen for most substances. So you might say that why not choose any two variables, but it is better. You can also see, especially with these two combinations, both pressure and volume are mechanical variables. In the same way, both temperature and S are in some sense associated with E. And that is why clearly that separation is there here when I write as PE is PES minus PEV. Clearly I am separating the mechanical part, contribution to the internal energy, from the contribution arising out of heat, right? So both P and S are associated. So you can see from a point of view of elegance, it doesn't seem proper, right? That you're choosing two mechanical variables and saying that that is sufficient to specify the state of the system. Really, anomalous expansion of water is one case where this is not proper. So the point is, why play around with something if which doesn't work, we know in a particular case, this is an isolated case. So better off sticking to these 4 sets of variables. This will be very important in the derivation of the so-called phase rule, because often phase rule there's a confusion, as to what the variables are. Some would say, or in any set of intensive variables is sufficient. How many intensive variables? The point is not whether it's intensive or extensive. We will stick to intensive and specific variables. It has to be very clearly stated in terms of what particular sets of variables are feasible as specification, right? And there, when you see, if you want to really prove a phase rule, it's important to stick to particular sets of